We can go back and cover some loose ends. Here is acetate, which you made in the lab yesterday when you titrated acetic acid. And the interesting thing about this is that I can draw these electrons jumping down here and these jumping out, so it can move that negative charge around. And I like to talk about a charge delocalization, with HBr being a stronger acid than HF, because bromine's so large and that negative charge can get distributed over a larger area. And when you drew Lewis structures, you do different resonance, where the difference between one resonance structure and another one is only the placement of electrons. So we failed to hit Lewis acids and bases, and they're defined in terms of electrons. Lewis acids are electron pair acceptors, and so something like this bromine here, which we say has an empty valence orbital, can behave as a Lewis acid. Here shortly we're going to look at metal cations can behave as Lewis acids. And then of course a Lewis base is pretty easy to spot because you will see lone pair electrons. So these lone pair of electrons find this boron nucleus, form a new covalent bond. And here we see an orbital diagram where we can see the unused orbital and how these electrons in nitrogen are stuck in a sp3 hybrid orbital, and then this overlap forms a covalent bond. What would I name this compound? Absolutely, aluminum nitrate. Now, nitrate renders things soluble, and if I put this in water, we might draw a picture that looks like this. And that might be good. However, it's a little oversimplified. What did you learn from the chapter on solution formation? The solvent has to do what with the solute? Has to solvate it, right? So it turns out when we have aluminum in solution, that 3+ charge attracts the negative end of a water molecule. So now I'm drawing a solvated water molecule. Excuse me, I'm drawing a solvated aluminum atom. If I did this right, I can draw something that looks like this. Now this charge is enough that we say hydrolysis can occur. And when the hydrolysis occurs, one of these water molecules breaks apart, and something like this occurs. So you can see I have one less water molecule because one got tore apart and gave me an OH and gave me a hydrogen ion. Of course, in solution, this is going to exist as hydronium. So maybe I should put another water molecule out here to make it balanced. You take aluminum nitrate and dissolve it up and make a solution. These ions become solvated, and then this hydrolysis, the splitting of water, can occur, and you get this little reaction. So here's what I just shown. So here's an aluminum, 6 water molecules around it. Small, highly charged metal ions can react with water to produce an acidic solution. I failed to put my charge. And some metals are more capable of this than others. So bromothymol blue is an acid-base indicator. It has different colors at different pHs. And here is sodium nitrate. When I think about sodium nitrate, I think about my solubility rules and how sodium rendered everything soluble. There's not an insoluble sodium compound. Same thing with nitrate. So that kind of tells me perhaps this chemistry is very spectator ion-like. Not much occurs. The nitrate can't act like an acid or base, and the sodium doesn't do what we saw aluminum do. So now we get to cadmium. And unfortunately, I don't know what concentration these are. I think they're fairly concentrated. We see this thing becoming slightly acidic, and then here's zinc, and here this aluminum nitrate. That's a pretty acidic solution. So a lot of your D block metals like copper, iron 3, they can all work as what we call Lewis acids. I think of a lot of these iron 3, a lot of these salt solutions in water are going to make things acidic, like one you've worked with in lab. Copper sulfate pentahydrate, a beautiful blue crystal. You make a solution of that, it's going to go acidic. And you might look here and see nothing that's too acidic, but sulfate's going to behave a lot like nitrate, just hang out and be a spectator ion. But this copper 2+ will become hydrated. I have no idea how many waters of hydration. We just go ahead and put 6, and then it encounters some water. It can split that water in half, and so the charge gets, it's almost like delocalizing the charge. Now there's this hydroxide in there. You have kind of a less positive charge. That might be a driving force for hydrolysis. So what are some other interesting acid-base properties of metals and maybe nonmetals? About this time, I like to talk about, I used to have a nice demo for this. What happens when you go into shock? Any A&P type people, medical type people? Anybody heard of acidosis? So when you go into shock, your breathing gets messed up and you don't remove CO2 from your body. So CO2 is a non-metal oxide. What type of acid-base property do you think it has? So I'm all scared and I'm breathing real shallow. Maybe I have something horrible going on. So this gas starts to build up in my bloodstream. And then I have this thing here. And when I look at this, it looks like I see this thing called carbonate. And I see these hydrogens stuck there. So what's the proper name for this? Absolutely. So then your blood pH gets real messed up. So the other day, Caden said a buffer is like a protection. So there's all these buffers in our body that protect us from pH getting out of whack. So in your body, there's a buffer based on carbonate. Now I just remember from all these dumb like TV shows like Emergency or MASH or whatever, Trapper John, when they get some trauma victim in and they're in shock, what do they normally give them? Yeah, they say, I want an IV of Bicarb stat. So they start pumping this into you, and it helps.
So it's the buffer with the gas.
Right. So this is building up, and your blood pH is kind of bad. They can just dump a lot of this into your body, stabilize your pH. All right. So we might call this a non-metal oxide, and most of these are acidic. What's so wonderful about Wyoming coal? Tax revenue for our state. Why is it better than West Virginia coal? Nah, the coal has a low sulfur content. So when you burn sulfur, you get things like sulfur dioxide, and floats up into the upper atmosphere. And you can also get sulfur trioxide. And so what do you call this? I call it acid rain. So, have you heard of acid rain before? It was a big thing back in the 80s when I was a kid. And then oxides of nitrogen, there's a whole slew of them. But when your car sucks in atmosphere, which is 80% nitrogen, and in the hot engine you can form some of these. So normally there's a catalytic converter that tries to knock some of this down. What acid is that? Nitric acid. So all these non-metal oxides have an acidic property. So oxides of metals and non-metals. So I've talked about these two a little bit. Carbonic acid from oxide of carbon. Sulfuric acid from an oxide of sulfur. Now metal oxides. Here's sodium oxide. Encounters water and you form some sodium hydroxide. Here's barium hydroxide. Barium oxide, presence of water, forms barium hydroxide. So metal hydroxides are basic, non-metal oxides are acidic. And we see that these reactions, here's a non-metal oxide and a base, and that looks like the same products, as if we titrated carbonic acid with sodium hydroxide. This thing here, now we have metal oxide, which is typically basic, and we get almost the same products as if we titrated barium hydroxide with nitric acid. So here's a nice periodic table. All these metal oxides with water are going to be what we call a basic oxide. All these non-metal oxides are going to be acidic. And then we have some weird ones here, which are amphoteric. What does amphoteric? They can act as either an acid or a base. Let's go back to the beginning of the semester when you were in lab. What are the products in this reaction? Mg. Now notice I have a compound and a single element. So the key is that word single. Yeah, single replacement. So magnesium is going to replace hydrogen. All right, and then we might look up at the periodic table, figure out we need a 2 there. It's going to force me to put a 2 there. And I said it was an excellent lab because it would segue into subject material later on in the semester. So notice I have an element by itself. What do you know about when I just have an element in its normal elemental state? What is its oxidation state or valence? What is the oxidation state of an element in its normal elemental form? What did you say? Absolutely. 0. I want to put a 0 here. And over here, it's Mg2+. So how do I balance charge? Yeah, plus 2 electrons. Where do those 2 electrons go? Right, so if I draw 2 electrons, notice I have a positive 2 and a negative 2, and we call these two things half reactions. Here's one half, here's the other half. How many of you have ever heard of Leo? Leo, the line goes grr. Right, so the first time I ever said that when I got here, people scowled and said, this is an oil town. We don't do Leo goes grr, we do oil rig. Oxidized, it loses. Let me put my oil rig up here. Reduced, it gains electrons. Oxidized, it loses electrons. So now here's a better question. What is the reducing agent and what is the oxidizing? Right, reducing agents get oxidized. They supply the electrons. And so what is the oxidizing agent? The proton. So what is electrochemistry? I like to think electrochemistry is using electricity to do chemistry, or using chemistry to make some electricity. Well, it's a lot of things. The relationship between electricity and chemical reactions. What is electricity? Electrons flowing in a wire, moving around doing things. What is a chemical bond? Normally a pair of electrons. So yeah, there's got to be a big relationship between electricity and chemical reactions. So here's our oil rig. Oxidation, reduction reactions, mouthful, so we like to say redox reactions. Oxidation involves loss of electrons. And also this number line. Kind of like the number line. I like it so much I'm gonna draw a number line now. Pretend I'm in math class. If I move this way, that's going to be called oxidation. And whenever I move this way, we're going to call that reduction. And so here we see going from 0 to positive 2, that's oxidation, an increase in oxidation number. How's that occur? By losing electrons. Here we are at a +1, and we went to a 0. What about these negative numbers? I need something that has a negative number in it. How about pull out a halide? Where do we think we want to write electrons? Well, this goes from negative. Here's an element in its elemental form. Yeah, it's oxidation. So somehow -2 on this side. I'll write 2 electrons over there. And as I just quizzed you a little bit, magnesium's the reducing agent. The protons are the oxidizing agent. Zinc metal's fairly active, just like the magnesium. If you put zinc metal in a solution of acid, you're going to see it fizz. Fizz is hydrogen gas. You can see protons being reduced, going from +1 to 0. You see the zinc going from 0 to +2. And Nick nailed this when I asked him. What is reduced is the oxidizing agent. This proton oxidizes zinc by taking electrons from it. What is oxidized is the reducing agent. Zinc reduces hydrogen by giving it an electron. So our equations thus far have been fairly straightforward. And some of these little half reactions, you heard me say, well, to make this balanced charge, I got a +2 over here, I need a +2 over there, or there's no charge, I need no charge. What am I going to do? So just as important as conservation of mass law, that matter is not conserved, we have this conservation of charge. We can think of as being electrons are not lost or gained in chemical reactions, and so conservation of charge. Half reactions. Why do we need half reactions? Half reactions are a convenient way of separating oxidation and reduction reactions. So here is presumably a redox reaction. Looks like a lot going on. And the question is, which element is reduced? So I asked a question at the beginning, which can really help you out, because there's a lot of rabbit holes on this thing to go down, like trying to figure out the oxidation state on iron. It's not trying to do that. But what did I say earlier with the magnesium or the hydrogen? Anything in its elemental state has an oxidation state of what? 0. What's the oxidation state of hydrogen here? So somehow we have 2 electrons are supplied. Now what would be more interesting and a lot harder, we won't do it, is what got oxidized. Which element is reduced in the reaction below? That is moving that way on the number line. That is oxidized, but that might help us figure something out. Let's do this. Is this thing charged balanced? No, so how do I get it to have the same charge on each side? I think I gotta supply an electron there. Alright, what about hydrogen? Well, here hydrogen's in the +1 oxidation state. What is hydrogen over here? Let me just refresh your memory. Oxygen's in that column there, 6th column, forms oxide -2. So hydrogen didn't do anything. Must be chromium. And so this is one of my favorite. You will recognize this as the dichromate anion, which is a powerful oxidizing agent. Why is it a powerful oxidizing agent? Well, let's figure out the oxidation state of chromium. How do we do that? We're going to call chromium X, and we got 7, and oxygen's going to be our guide. Oxygen is normally -2. These must sum up to the charge found on the polyatomic ion. So that's how you want to set this up. So I have 2x -14 equals -2. I'm going to add 14 to each side to get 2x plus 14, and a -2 is a +12. Divide both sides by 2. So over here we have chromium +6 oxidation state went to the 0. Chromium got reduced.